In this video, we're going to explain how some of the constructions that we've done on Rn translate to manifolds. So we're going to talk about tangent vectors, differential forms, and orientations. So let's just recall how we construct the tangent space to a manifold. So the tangent space to a manifold M at a point P is the vector space of equivalence classes of smooth curves, gamma from R, or maybe from some subset of R to M, with gamma at 0 equal to P, and we say gamma 0 and gamma 1 are equivalent if their derivatives at the point at 0 are equal to each other. So what gamma being valued in M means is just it's a map to our M, the ambient space of M, the Euclidean space that M lives in, and it's just values are taken in M. And this, we denote the space by TPM. And remember, so I may have defined this, but I'll say this again. A differential, it's a little bit different than in the case of Euclidean space. A differential K-form on M is a map, it's a map from M to another space of maps. So it's a map which takes each point in M to a map which takes K tuples in TPM, so K tuples of vectors to real numbers. So basically, you can just think of these locally. So locally, we write K-forms in coordinates. So if I have phi inverse parameterizing my manifold as some phi inverse pullback of alpha, which is just a K-form on Rn, or Rm, or sorry, Rn, because phi inverse is from Rn. Or we'll often, if M sits inside Rm, we write alpha in coordinates on Rm. So generally, sort of the complication in studying these forms will just be translating between these two perspectives on how to write down a K-form on a manifold M. So the next thing that we like to do to K-forms is take their exterior derivatives. So this is sort of a theorem / definition, and you can see for the proof you can look at Spivak. We're actually going to prove this, so you can read it in Spivak or just watch the rest of this video. So there is a unique K+1 form. So given any K form alpha, there's a unique K+1 form d alpha on M. Which is defined so that in each coordinate chart, phi inverse pullback of d alpha is equal to d of phi inverse pullback of alpha. Equivalently, this is the same thing as defining d alpha to satisfy the following equation. D alpha is phi pullback applied to d of phi inverse pullback of alpha. And the reason why we have to go through all this rigmarole is that we don't really understand how to compute d of a K-form if we have alpha written in some abstract way. Like, it's not necessarily the case that alpha is written in local coordinates, or if alpha is written in coordinates on the large Euclidean space, computing its derivative might give you something that, for example, is non-zero in the larger Euclidean space, but is actually 0 as a form on the manifold. So we actually do, you can't just compute d alpha as a form on the larger space. You have to go through this definition here. Okay, so so what do we need to prove here? Basically, we need to prove that if we have two coordinate charts whose ranges overlap. So if I have my manifold M and I have like U and U prime, and I have some map, let's say the map goes this way. So this is a map B inverse going from Rn, from some subset of Rn to U, and then I have psi inverse going from some subset of Rn to U prime. I need to show that this definition is well defined on the overlap. So I need to show that if I define D using this equation, that it doesn't matter what coordinate chart I used. So I need to show that phi inverse pullback of d alpha is equal to the same thing as, sorry, I should use the second equation. So I need to show that the second equation is equal to what I would have gotten if I had written it down using psi. So psi pullback d psi inverse pullback of alpha. Okay, so this is, however, this is equivalent to composing both sides with psi inverse pullback, because psi is one-to-one onto M intersect U, right? So this is, maybe I'll write, this is M intersect U and M intersect U prime. So I can just compose both sides with psi inverse pullback. So it's psi inverse pullback, V inverse D, V inverse pullback alpha equals D of psi inverse pullback alpha. Okay, that's what I want to show now. And then I just need to simplify this left-hand side. So because D commutes with pullback on Euclidean space, and okay, so here's something to maybe an aside. Psi inverse pullback, phi inverse, is equal to phi composed with psi inverse pullback. This follows from a problem you showed on your homework. And phi composed with psi inverse pullback is a map from, or sorry, phi composed with psi inverse is a map, so phi goes this way. So it's going to go from, so, and it will be defined in this overlap space. So it will go from Rn through, let me actually use a different color. It'll go from Rn through psi inverse to the overlap of M intersect U and M intersect U prime. And then it will use phi to go back to Rn. So in the end, this composition is just a map from Rn to Rn. And I can use the fact that D commutes with pullback for maps from Rn to Rn to rewrite this left-hand side as D of psi inverse pullback, phi pullback, phi inverse pullback. And then now these cancel out because these are just two. So when I actually compute this thing, I'll just have two matrices which are inverses of each other, multiplying by anything that I'm inputting into alpha. So these just disappear, they cancel out, and I get that this is D psi inverse pullback of alpha, which is exactly what I wanted because that's what I have here. So I've shown that this equation, D of psi inverse pullback alpha is equal to itself, is equivalent to what I wanted to show. So then the way that I define D of a differential form on a manifold is using this equation, or this equation if it's easier. Okay, so the final thing to talk about are orientations, because this is crucial for defining integration. So an orientation on a vector space is an equivalence class of bases. So where we say that V1 through Vn is equivalent to a basis W1 through Wn, if the determinant of the change of basis matrix, let me put this on a line below, is positive. So as an example, on R2, if R2 is my vector space, then if I consider like the vector that points in the x direction and then the vector that points in the y direction, if this is my first vector and this is my second vector, I like to label the vectors with 1 and 2 just so that you know which is which. This is the same orientation as, for example, this orientation here. But it's the opposite orientation to the one that's represented by, for example, just switching the y direction vector to come first and then the x direction vector to come second. So here, let's show this. So basically this is because the change of basis matrix in this case is going to be 0, 1, 1, 0, and the determinant of this thing is -1, which is less than 0. And because whether a basis is equivalent, or a basis is equivalent to 1 or not based on the sign of the determinant of this matrix, you can see that there are just two orientations. There's either ones where this determinant is positive or ones where the determinant is negative. If you choose one basis, then either another basis will be equivalent to it or it will not be, and all of those that are not equivalent are all equivalent to each other. So there's always two orientations. On R3, we use the right-hand rule. So we use, as our standard basis, basically we think of this as 1, 2, 3. So using the right-hand rule, your fingers start in the direction of 1, curl in the direction of 2, and then your thumb will point in the direction of 3. And an orientation is also equivalent to a choice of volume form. So we say that two volume forms are equivalent. So a volume form is any, just any top dimensional form. So an n form on Rn, for example, if they measure the same inputs with the same sign. So I basically had a whole video about this. For example, dx wedge dy is equivalent to dr wedge d theta, but not equivalent to d theta wedge dr. And an orientation, so how are we going to soup this up to manifolds? An orientation on a manifold is a continuous choice of orientation on each tangent space. So it's an orientation on each tangent space, which are represented, or which can be represented by continuous vector fields. So, so for example, if I were to pick an orientation on a surface like the torus, for example, I would say, okay, maybe I'll choose some vector fields. I mean, and this continuous vector fields, this only has to be locally. So I don't need to be able to choose vector fields, sort of n vector fields over all of m that are always non-zero. They're always bases, but I just mean that locally. So if I'm picking 2 points, so say I pick an orientation that looks like that there, this is 1 and this is 2, then to get my orientation at a nearby point, what I need to be able to do is sort of include them in the same coordinate chart and then cover this thing with vector fields. So maybe I'll pick this vector field that's always pointing that way, and that will always be my sort of first one, and then I can always pick this vector field as my second vector. So this doesn't mean, and then so if a manifold has an orientation, it's orientable. And so this condition, remember, it's local, so I don't have to be able to pick these two vector fields globally, just locally. And otherwise, there would be far fewer orientable manifolds than there are. And if a manifold is orientable, there are two orientations, essentially for the same reason as for orientations on a vector space. And orientation are equivalent. An orientation is equivalent to a non-vanishing. So to non-vanishing n form, so orientations of n manifolds, are equivalent to choices of a non-vanishing n form up to multiplication by a positive function. So what I'm saying, for example, is that on R2, for example, dx wedge dy is going to be equivalent to, let's say, x squared dx wedge dy, but it's not equivalent to y dx wedge dy because y is not a positive function. This isn't even a volume form, that's just nothing. But it's also not equivalent to, for example, negative x squared dx wedge dy, because negative x squared dx wedge dy is the opposite, represents the opposite orientation. We're not going to get too into this, but there are non-orientable manifolds. So there's one you probably already know, which is the Mobius strip. And this is because it's not possible to pick a continuous orientation at each point. If you try and do this, you should be able to sort of go around the circle and pick the orientations consistently, but once you wrap back around, you won't be able to do that. So the final thing in this video that we want to talk about are boundary orientations. So if I have a manifold with boundary, an orientation on M determines an orientation on the boundary of M. So if I have an orientation on M, V1 through, well, let's not give it a name. So if I have an orientation, if I want to check whether V1 through Vn minus 1 is oriented on the boundary of M, with respect to this orientation determined by the orientation on M, I just need to check if new V1 through Vn minus 1 is an oriented basis on M. So I'm checking whether V1 through Vn is oriented on the tangent space to a point at the boundary of M. I need to check if new, so if when I extend this basis by some vector nu, which I'll define in a moment, is oriented on the tangent space to M at that same point, where nu is the outward pointing normal to the boundary of M. So this is called the outward normal first orientation on the boundary of M. So this kind of seems like a little bit of gobbledygook, but when you think about it on an example, it's really clear that this is what you should do. So if I think of the two-disk, and I think of what is an oriented basis, I should always have my first vector pointing. I should have the first vector, when I go from the first to the second, via the smaller of the two angles they define, I should be going counterclockwise. So I want to think about how to orient the boundary circle at this point that I've drawn. The outward normal should go first, and um, then the second vector, if I sort of slide it over, that's the vector that's tangent to the circle, which completes this basis, is the one that points counterclockwise. So what I end up getting is that if I want to, let me draw this in a different color, if I want to figure out what the orientation on the boundary induced by the orientation of the interior is, I should be pointing my vectors counterclockwise. And there are more complicated examples that we'll talk about in class than for the homework.